Welcome to this video. Today, we'll be tackling problem number 1990, count the number of quadruple pairs. This problem is both an interesting and challenging exercise in leveraging hash maps to optimize calculations for specific numeric conditions. Let's dive in and explore the solution together. In this problem, we are tasked with counting the number of distinct quadruple pairs in an integer array nums that satisfy specific conditions. A quadruple pair consists of four indices, I, j, k, l, such that the sums of the elements at indices I and j, and the sums of elements at indices k and l, both equal the given target value. Additionally, the indices must meet the constraints I less than j and k less than l. The challenge here is to determine how many such quadruple pairs exist in the array while adhering to these strict conditions. The input consists of an array nums with a length between 2 and 2000, where each element can range from -10⁻6 to 10⁻6, and an integer target that also falls within the same range. The output is a single integer representing the total number of valid quadruple pairs that satisfy the problem's requirements. To understand the problem further, let's look at the first example. Here, the input array is nums equals 1, 2, 3, 4, 5, and the target value is 5. The output is 2, which represents the total number of valid quadruple pairs. The two pairs are 0, 3, 1, 2, and 1, 2, 0, 3. For the first pair, the sum of nums 0 and nums 3 is 1 plus 4 equals 5, and the sum of nums 1 and nums 2 is 2 plus 3 equals 5, both matching the target. Similarly, for the second pair, the sums of the respective indices also equal the target. This example illustrates how the indices must satisfy both the numerical condition and the ordering constraints. In the second example, the input array is nums equals 1, 1, 1, 1, and the target is 2. The output here is 12, which is the total number of valid quadruple pairs. The pairs are 0, 1, 2, 3, 0, 2, 1, 3, 0, 3, 1, 2, 1, 2, 0, 3, 1, 3, 0, 2, and 2, 3, 0, 1. Notice that in this case, all values in the array are identical, which leads to a larger number of valid combinations since any pair of indices can produce the target sum. This highlights how the structure of the input array can significantly influence the number of quadruple pairs. In the third example, the array is nums equals 2, 2, 2, 2, 2, and the target is 4. The output is 60, representing all possible combinations of indices I, j, k, l that satisfy the conditions. Because all elements in the array are the same and equal to 2, any pair of indices will sum to the target, resulting in a very large number of valid quadruple pairs. Finally, the constraints remind us to consider edge cases, such as when the array has the smallest possible size, when all elements are equal, or when no pairs produce the target. For larger arrays, it's crucial to optimize the solution to handle the input efficiently, as a brute force approach with n to the power of 4, complexity would be impractical for the upper limit of nums.length. To solve this problem, the brute force approach is the most straightforward way to start. The intuition here is to iterate over all possible combinations of quadruples, I, j, k, l, in the array and check if they satisfy the given conditions. Specifically, we need to verify two things: first, that the indices follow the constraints I less than j and k less than l, and second, that the sums of the pairs I, j, and k, l both equal the target value. Implementing this approach involves using four nested loops to generate all possible index combinations and then filtering out those that meet the criteria. While this approach is simple to understand and implement, it comes with a significant drawback. Its time complexity is n to the power of 4, which becomes computationally infeasible as the size of the input array increases. For larger arrays, say with more than 100 elements, the exponential growth in computations makes this approach unsuitable, even though it requires minimal memory with space complexity. Now, to overcome the inefficiency of the brute force approach, we can turn to an optimized solution using a hashing technique. The key idea here is to reduce the number of combinations we need to check by leveraging a hash map to store the sums of all possible pairs. Instead of iterating over quadruples directly, we start by pre-computing the sums of all pairs, nums, x, plus nums, y, and storing these sums in a hash map. The hash map's keys are the pair sums, and the values are lists of index pairs, x, y, that produce those sums. This allows us to efficiently find and group pairs of indices whose sums match the target value. During the second phase, we use the hash map to quickly identify combinations of pairs that satisfy the conditions. Importantly, we ensure that the indices adhere to the constraints I less than j and k less than l as we process the hash map. This approach reduces the time complexity to O(n squared), as we're computing sums for all index pairs only once, and the space complexity is also O(n squared), due to the storage requirements of the hash map. This hashing approach offers a clear trade-off between time and space complexity. While it requires additional memory to store the hash map of pair sums, the significant reduction in runtime makes it a far better choice for larger input sizes. The reason this strategy was chosen lies in its efficiency. By reducing the problem from O(n to the power of 4 to O(n squared), we make it feasible to handle much larger inputs without compromising correctness. The key insight here was recognizing that the problem could be reformulated as finding matching pair sums, which the hash map enables us to do efficiently. This realization eliminated the need for nested loops to directly compare quadruples, simplifying the implementation and drastically speeding up the process. Comparing the two approaches, brute force is only viable for very small arrays due to its exponential time complexity, while hashing strikes an excellent balance, achieving significant performance improvements for a modest increase in space usage. In conclusion, the hashing approach is not only the most efficient solution but also retains simplicity in its implementation. By pre-computing pair sums and leveraging a hash map for efficient lookups, we achieve a dramatic reduction in computational cost. This makes the approach scalable and practical for real-world applications. The ability to reduce the problem to matching pair sums was the pivotal insight that allowed us to move away from the brute force method and adopt a strategy that is both fast and elegant. For problems of this nature, where multiple indices and constraints are involved, using data structures like hash maps to optimize lookups is a powerful technique that strikes the right balance between time and space complexity. In this problem, we are tasked with finding all quadruples of indices I, j, k, l in an array such that the sum of the elements at indices I and j equals the sum of the elements at indices k and l, and all indices are distinct. To break this down, the condition is nums I plus nums j equals nums k plus nums l. This means we are looking for two pairs of numbers whose sums match, but the indices of these numbers cannot overlap. Now, to approach this, we first need to understand the constraints. The input is an array of integers, and we need to ensure all indices I, j, k, l are unique. The challenge is to solve this efficiently. A straightforward way to tackle this is by using a brute force approach. This involves iterating over all possible combinations of indices using 4 nested loops. For every combination, we compute the sum of the pairs and check if they match. If they do, and the indices are distinct, we record the quadruple. However, this brute force method has a time complexity of O(n to the power of 4, which becomes impractical for larger arrays. Let's look at how we can improve this approach. To optimize the brute force solution, we can use a hash map to reduce the computational complexity. The idea is to pre-compute pair sums and store them in a hash map for efficient lookups. First, we construct the hash map, where the keys are the sums of pairs, and the values are lists of index pairs that produce those sums. For example, for every pair I, j, we calculate nums I plus nums j and store it in the hash map, appending the pair I, j to the list associated with that sum. This pre-processing step has a time complexity of O(n squared, since we iterate over all unique pairs of indices. Once the hash map is built, we can efficiently find quadruples by iterating through its entries. For every sum in the hash map, we take the list of index pairs associated with that sum and cross-check them to ensure the indices are distinct. If we find valid quadruples, we record them. This optimized approach reduces the computational burden significantly compared to brute force. However, we must also consider edge cases, such as when the input array is empty or has fewer than 4 elements, where no quadruples can exist. Additionally, for arrays with duplicate values, we need to ensure indices are validated independently of the values to avoid false positives. For large arrays, it's important to manage the hash map efficiently to avoid excessive memory usage. The optimization here lies in how the hash map allows us to pre-compute pair sums, reducing the sum computation step from O(n to the power of 4 to O(n squared). However, this improvement comes with a trade-off. The hash map requires additional space to store pair sums, resulting in a space complexity of n squared. To ensure our solution remains efficient, we must carefully validate indices when combining pairs from the hash map. This prevents invalid quadruples from being included. Using a hash map as our primary data structure is key because it offers constant time lookups for sums. Additionally, a list is used to store the final quadruples that meet the conditions. In terms of implementation, the pseudocode starts by iterating through all pairs of indices to compute their sums and populate the hash map. Each sum maps to a list of index pairs that produce it. Once the hash map is ready, we then iterate through its entries to find combinations of pairs that meet the quadruple criteria. At this stage, we ensure all indices are distinct before adding the quadruple to the result. The pseudocode continues by validating the indices of the pairs from the hash map. For each pair of indices, I, j, and k, l, associated with the same sum, we check that I, j, k, and l are distinct. If they are, we add the quadruple, I, j, k, l, to the result list. This validation ensures the correctness of our solution. When analyzing the time complexity, the pair sum pre-computation takes n squared, and the quadruple validation step involves iterating through the hash map and cross-checking indices, which also takes n squared. Therefore, the overall time complexity of the optimized approach is n squared. In terms of space complexity, the hash map requires n squared to store all pair sums, and the output storage depends on the number of valid quadruples, denoted as k. Finally, the key optimizations in this method involve avoiding redundant computations by pre-computing pair sums, leveraging the hash map for efficient lookups, and minimizing space usage by only storing necessary index pairs. This makes the algorithm significantly more scalable compared to the brute force solution. This solution efficiently counts the quadruples, I, j, k, l, in the array nums such that nums, I, plus nums, j, equals nums, k, plus nums, l, and all indices are distinct. The key idea is to use a dictionary sum_map to store the sums of pairs of elements as keys and their corresponding index pairs, I, j, as values. Explanation. 1. Initialization. We initialize an empty dictionary sum_map to store sums and their corresponding index pairs. We also set count to 0, which will store the total number of valid quadruples. 2. Iterate through all pairs of indices. We loop through all possible pairs of indices, I, j, in the array, ensuring I less than j to avoid duplicate pairs. This is achieved by using nested loops, where the inner loop starts at I plus 1. 3. Calculate pair sum. For each pair, I, j, we calculate the sum nums, I, plus nums, j. Check for existing sums in the map. If the sum already exists in sum_map, it means there are previous pairs, k, l, such that nums, k, plus nums, l, equals the current sum. We iterate over these pairs and ensure all indices are distinct using len, set, I, j, k, l, equals 4. If valid, we increment the count. 5. Add the current pair to the map. After processing, we add the current pair, I, j, to the list of pairs for the current sum in sum_map. If the sum is not already in the map, we initialize it with an empty list. 6. Return the result. After processing all pairs, we return the count of valid quadruples. Complexity. Time complexity. The algorithm uses nested loops over all pairs, resulting in n squared iterations. For each pair, the sum lookup and addition are 1. Thus, the overall complexity is n squared. Space complexity. The space required for sum_map can grow to n squared, in the worst case, where all pairs have unique sums. This implementation is efficient for moderately sized arrays and avoids a brute force n to the power of 4 approach by leveraging the sum map for optimization. Here, we begin by importing the necessary Java utilities and defining our solution class with the method countQuadruples. This method takes an array of integers, nums, as input and returns the count of valid quadruples. To solve the problem efficiently, we utilize a hash map called SumMap, which stores the sums of pairs of numbers as keys and their corresponding index pairs as values. We also initialize a variable, count, to keep track of the number of valid quadruples, and determine the length of the input array, n. Next, we use a nested loop to iterate through all possible pairs of indices I and j, ensuring that I is less than j. For each pair, we calculate their sum, pair sum. If this sum already exists in the map, we retrieve the list of index pairs associated with it and iterate over them. For each existing pair, represented by indices k and l, we check if all indices I, j, k, and l are distinct. If they are, it means we have found a valid quadruple, so we increment the count. After processing any potential valid quadruples for the current pair sum, we then update the sum map. If the pair sum key does not exist in the map yet, we initialize it with an empty list. We then add the current index pair, I and j, to the list associated with this sum. By doing so, we ensure that future pairs can reference this information to form new quadruples. Once both loops complete and all pairs have been evaluated, the count variable will hold the total number of quadruples satisfying the problem's requirements. Finally, we return this count as the result. This approach leverages the hash map to officially track and query pair sums, ensuring that we don't repeatedly compute the same information. To solve this problem, we start by initializing a few key variables. First, we create an empty dictionary called sum_map. This will store the sums of pairs as keys and the corresponding index pairs as values. Then, we initialize count to 0, which will keep track of the number of valid quadruples. Lastly, we set n to the length of the input array nums, which is 5 in this example. With these variables in place, we begin iterating through all possible pairs of indices, I, j. For the first outer loop where I equals 0, we go through each j value greater than I. For instance, when j equals 1, we calculate the pair sum as nums, 0, plus nums, 1, which equals 3. Since 3 is not yet in sum_map, we add the pair, 0, 1, under the key 3. Similarly, for j equals 2, we compute the sum as nums, 0, plus nums, 2, which equals 4, and add 0, 2, to sum_map, 4. This process continues for j equals 3 and j equals 4, adding 0, 3, to sum_map, 5, and 0, 4, to sum_map, 6, respectively. By the end of the first outer loop, sum_map contains the sums 3, 4, 5, and 6, each mapped to the relevant index pairs. Now we extend this process for all other values of I. For each outer loop iteration, we calculate the pair_sum for all valid I, j pairs and update sum_map accordingly. By the time we finish iterating through all combinations of indices, sum_map contains every possible pair sum as keys, with their corresponding index pairs as values. For example, after processing all pairs, sum_map might look like this: 3 maps to 0, 1, 4 maps to 0, 2, 1, 2, 5 maps to 0, 3, 1, 3, and so on. With sum_map fully populated, we then move on to counting valid quadruples. The idea is to loop through each pair_sum and sum_map and examine all combinations of index pairs, I, j, and k, l, associated with that sum. For every such combination, we check if all 4 indices are distinct by ensuring the set of indices has a length of 4. If this condition is satisfied, it means we've found a valid quadruple, and we increment the count. After completing the iteration and checking all combinations, we update the count variable for any valid quadruples identified. For nums equals 1, 2, 3, 4, 5, there is exactly one such quadruple, namely 0, 1, 2, 3. Therefore, the final value of count is 1. This concludes the first example. Now, let's explore a second example with nums equals 1, 1, 1, 1. Again, we start by initializing sum_map as an empty dictionary, count as 0, and n as the length of nums, which is 4. As before, we iterate through all possible pairs of indices, beginning with I equals 0. When j equals 1, the pair sum is nums, 0, plus nums, 1, which equals 2. Since 2 is not in sum_map, we add 0, 1, to sum_map, 2. Similarly, for j equals 2 and j equals 3, we compute the same pair_sum of 2 and add the pairs 0, 2, and 0, 3, to sum_map, 2, respectively. Next, we continue calculating pair_sum for all remaining pairs of indices and updating sum_map accordingly. By the end of this process, sum_map for nums equals 1, 1, 1, 1, contains only one key, 2, which maps to the pairs 0, 1, 0, 2, 0, 3. Now, we move to counting valid quadruples. For the pair underscore sum of 2, we iterate through all combinations of the stored index pairs, such as 0, 1 with 0, 2, or 0, 1 with 0, 3. However, in each case, we find that the indices overlap, meaning the same index is used more than once. Since the problem requires all indices to be distinct, no valid quadruples are found in this example. As a result, the count remains 0. Thus, the final output for this input is count equals 0. Now, let's consider a third example where nums equals 2, 2, 2, 2, 2. For this example, we again start by initializing some underscore map, count, and n. Here, n equals 5. As before, we calculate pair underscore sum for all possible pairs of indices, I, j, and update some underscore map. Since all elements in nums are the same, every pair produces the same pair underscore sum of 4. As a result, sum underscore map 4 accumulates all the index pairs, such as 0, 1, 0, 2, 0, 3, 0, 4, 1, 2, and so on. Once sum underscore map is populated, we proceed to count valid quadruples. For the pair underscore sum of 4, we examine all combinations of the stored pairs and ensure that all indices in each combination are distinct. For this input, we find 5 valid quadruples 0, 1, 2, 3, 0, 1, 2, 4, 0, 1, 3, 4, 0, 2, 3, 4, and 1, 2, 3, 4. Thus, the final value of count is 5. This demonstrates how the solution handles cases with repeated elements effectively. Here, we analyze the time complexity of the solution step by step. The algorithm uses nested loops to iterate over all pairs of indices, I, j, or I less than j. The total number of such pairs in an array of size n is given by the combination formula C, n2, which simplifies to n asterisk, n1/2. As a result, the outer loops execute in O, n squared, time. For each pair, I, j, the algorithm checks if their sum already exists in the dictionary, sum underscore map. If it does, the algorithm iterates over all previously stored pairs, k, l, for the same sum. In the worst case, we may have O, n squared, stored pairs for a given sum, which means this step could take significant time depending on the input distribution. Finally, adding a new pair, I, j, to sum underscore map is an O1 if operation, but since it's repeated for all pairs, this contributes another O, n squared, overall. Combining these steps, we'll explore the total time complexity further. To determine the total time complexity, we consider the worst-case scenario where for each pair, I, j, the algorithm must process all previously stored pairs in sum underscore map. This results in a worst-case time complexity of O, n to the power of 4. However, in practice, the performance often depends on how the sums are distributed and how many pairs map to the same sum. Now, looking at the space complexity, the dictionary sum underscore map stores all unique sums of the form nums, I, plus nums, j, along with the pairs, I, j, that produce these sums. In the worst case, there could be O, n squared, pairs, and since each pair is stored as a tuple, the space required to store these pairs is O, n squared. Additionally, the algorithm uses only a constant amount of extra space for variables like count, pair underscore sum, and the indices I, j, k, l, which adds O1 to the space complexity. Therefore, the total space complexity is dominated by the storage in sum underscore map, making it O, n squared. When comparing the current solution to a brute force approach, we can see the improvement. A naive solution would involve iterating over all quadruples, I, j, k, l, directly, checking if the sums of two pairs are equal while ensuring all indices are distinct. This requires iterating over C, n, for quadruples, resulting in a time complexity of O, n to the power of 4. The current solution optimizes this by using a dictionary to store and reuse pair sums, avoiding the need to explicitly iterate over all quadruples. Despite this optimization, the worst-case time complexity remains O, n to the power of 4, as the algorithm might still need to process a large number of pairs for the same sum. The best-case scenario occurs when the sums are highly unique, minimizing the sum underscore map lookups and processing steps. In this case, the time complexity can reduce to O, n squared. However, in the worst case, where all sums collide, such as when all numbers are the same, the algorithm has to process all stored pairs for each new pair, leading back to O, n to the power of 4. To summarize, the time complexity of the current solution is O, n to the power of 4, in the worst case and O, n squared, in the best case, depending on the distribution of sums and the number of collisions in the sum_score map. The space complexity is O, n squared, dominated by the storage of all pairs in the dictionary. While this solution significantly improves over a brute force approach in many practical cases, it still suffers from high complexity in the worst case due to overlapping sums. This trade-off highlights the importance of understanding the input distribution when evaluating the performance of the algorithm. One of the most common mistakes when solving this problem is mishandling indices. Remember, the indices I, j, k, and l must always be distinct. In some cases, additional constraints like I being less than j, j less than k, and so on might be imposed, so it's crucial to understand the specific rules before diving into a solution. Another pitfall is relying on a brute force approach, which involves iterating over all possible quadruples. While straightforward, this results in a time complexity of O, n to the power of 4, which is impractical for large arrays. Instead, you should focus on optimization techniques, such as using hash maps to store pair sums. Additionally, care must be taken to avoid duplicate counting. For example, if you're storing sums in a hash map, it's easy to mistakenly count the same pair of indices multiple times. To prevent this, ensure that you're only considering valid, distinct index combinations. Finally, don't overlook edge cases. For instance, what happens if the array has fewer than 4 elements, or if there are duplicate numbers? These scenarios must be handled carefully to avoid incorrect results. Similarly, when using hash maps, mismanaging keys or overwriting values can lead to corrupt solutions, so clear data structures like lists should be used to store index pairs for each sum whenever possible. When tackling this problem in an interview, it's important to discuss complexity early. Brute force solutions are usually unacceptable due to their inefficiency, so you should quickly acknowledge this limitation and propose optimized approaches, like using a hash map to store pair sums. This demonstrates your ability to analyze and improve the algorithm's performance. Another key insight is recognizing that the problem is essentially about matching pairs that satisfy a condition, such as a target sum. Hash maps are particularly effective here because they allow for efficient lookups and storage, making them a natural choice for solving this type of problem. Always make sure to clarify the constraints with the interviewer. For instance, do the quadruples need to be distinct? Are there any specific bounds on the size of the input array? These questions help refine your solution and avoid unnecessary mistakes. Additionally, be prepared to discuss the trade-offs between time and space. While hash maps can greatly reduce time complexity, they do require significant memory. A good interview answer will address these trade-offs and show that you've considered the implications of your chosen approach. This problem has connections to several related problems that can help deepen your understanding. For example, the two-sum problem, which is LeetCode 1, is a foundational exercise in using hash maps for sum-based problems. Here, you learn the basics of efficient pair matching. Moving up in complexity, the three-sum problem, LeetCode 15, involves finding triplets that meet a target sum. This introduces techniques like sorting and the two-pointer approach, which are also valuable for problems involving multiple indices. Then there's LeetCode 18, the four-sum problem, which is closely related to this one. While the constraints might differ slightly, the general idea of identifying valid quadruples remains the same. Lastly, there's equal row and column pairs, LeetCode 2352, which uses hash maps in a different context, pairing rows and columns in matrices. Exploring these problems can provide a broader perspective on how to apply similar techniques in various scenarios. There are several alternative approaches to solving this problem, each with its own trade-offs. One popular method is optimized hashing, where you store pair sums in a hash map. The key is the sum, and the value is a list of index pairs. This reduces the time complexity to O, n squared, but it does come at the cost of O, n squared, space. The trade-off here is clear: faster computation versus higher memory usage. Another approach involves sorting the array and using two pointers. This works particularly well if the problem involves sorted arrays or constraints like distinct elements. While this method can reduce complexity in certain scenarios, it's less flexible when arbitrary indices are required. Finally, there's pre-computation, where you calculate all pair sums and sort them. This simplifies pair matching later but has its own costs, specifically O n squared, space and O n squared log n time. Each approach has its strengths and weaknesses, so your choice should depend on the problem's constraints, the size of the input, and the trade-offs you're willing to accept. Great job! We reviewed the problem, explored approaches, and highlighted key optimization techniques. Remember, mastering these concepts takes practice, so keep challenging yourself with similar problems. Thank you for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!